So in this section here, we're going to look at some special second order differential equations and we're going to solve them. These types of equations that we're going to be looking at are commonly used to model vibrations. So you may have seen, say, a vibration of a string or a spring in your physics class. Maybe you've used Hooke's law. That's all second order differential equations. And there's special types of second order differential equations. They're going to be second order linear differential equations. So when we talk about a second order linear differential equation, it has a very specific form. First of all, notice in this general form, we have our second derivative, we have our first derivative, and we have our function y that we're trying to solve for. Now, since this is a differential equation, the coefficients on the derivative in our function y, they can be functions of x. But remember, they cannot be functions of y or its derivative, or else it's no longer linear. So the p of x, q of x, r of x, and even this g of x, these are just continuous functions with respect to the variable x. Now, if g of x, if what this equation is equal to is actually 0, so if this equation is equal to 0, then we call it a homogeneous equation. If it's not equal to 0, then it's non-homogeneous. For this particular section, we're only concerned with homogeneous second order linear differential equations. So that just means that our differential equations are going to be equal to 0. And those are much simpler to solve. Once you get into the non-homogeneous second order differential equations, they become much more complicated. So that would be a topic that is reserved for your actual differential equations class, maybe Math 307 if you're taking Math at Manoa, or Math 302. So what follows from this definition of second order linear differential equations is going to be some other theorems and definitions. So the first theorem we're going to look at just says if you have two solutions, y sub 1 and y sub 2, and they're solutions to a linear homogeneous equation, and then let's say also that we have this c sub 1, c sub 2. These are just some constant real numbers. Then if you combine these two solutions and you multiply them by these constants, you'll get this new function y of x. And this function y of x, that is simply the addition of these two solutions multiplied by these constants, they will also be a solution to that linear homogeneous equation. Okay, so all this is saying is that if you have solutions, then you can add them together or you can multiply them by constants and the result will still be a solution. Right, so we're going to look at this definition now and it's going to classify our solutions. So let's say that we do have two solutions. We say that the solutions are linearly independent solutions if they're both solutions to the same homogeneous linear equation, and neither of the function is a constant multiple of each other. Okay, so this y sub 1, y sub 2, both solutions to the same equation, but they're not multiples of each other. And that's nice if you do have linearly independent solutions. Okay, so we have this other theorem, and it says if you happen to have two solutions that are linearly independent, so this theorem follows from that previous definition, and your p of x is not equal to 0, so going back to the general form, remember p of x is the coefficient on your second derivative. So as long as that's not equal to 0, then your general solution to your differential equation is given by this function, which is simply y of x that we looked at in the definition, where we take our two solutions, they could be multiplied by some constant, and we simply add them together. So this y of x equal to c sub 1, y sub 1 plus c sub 2, y sub 2, that would be the general solution to our second order linear differential equation as long as the p of x is not equal to 0. And here again, the c sub 1, c sub 2, they're just constants. Again, as a reminder, solving differential equations can be tricky because remember, you're trying to get rid of derivatives, which means you need to do the antiderivative or you need to integrate. And since integration involves a lot of different techniques, it depends on the type of integral you have. We have a lot of special techniques to solve differential equations as well. So again, in this section, we're just going to focus on second order linear differential equations that are homogeneous. And in fact, we're going to even simplify it further. If we look at these 2 bullet points, I had just mentioned that it's difficult to find solutions to second order linear equations. But we're going to look at the special case where P, Q, and R are not simply functions of x, they're actually constant real numbers. Okay. Then our second order homogeneous equation is going to be of this form here. A times the second derivative plus b times the first derivative plus c times the function equal to 0. That's what it'll look like. If so, then y equal to e to the rx, and r can just be any number, that's going to be a possible solution to this type of second order linear homogeneous differential equation. That's getting too long. So what we're going to do is say, okay, that's a possible solution. Well, what conditions have to be met in order for this to be a solution, okay, to this very specific type of differential equation where the coefficients on the derivatives and on the function y are just constant real numbers? Well, all I'm going to do is I'm going to take this differential equation and I'm going to substitute in the second derivative, the first derivative, and y. Now I already have my possible y value. If I simply take its derivative and its second derivative, I can just plug those into the equation and see what my a, b, and c have to look like in order for them to be solutions. So if y is equal to e to the rx, then the first derivative is r times e to the rx. And the second derivative is r squared e to the rx. I'm going to plug that in this equation. So it's a times second derivative is r squared e to the rx plus b times first derivative is r e to the rx plus c times our function y is e to the rx. And this equation is equal to 0. So what do my a, b, and c have to look like? Well, I can see on the left-hand side that I have a common factor, e to the rx, that I could factor out. What's left over is going to be a r squared plus br plus c. So that should look familiar. It's just a quadratic equation. However, on the left-hand side, I have a factored expression equal to 0. So algebraically, it must be true that either e to the rx is equal to 0 or ar squared plus b times r plus c is equal to 0. And now e to the rx can never be equal to 0. It doesn't matter what that exponent is on your base e, it'll always be some non-zero number. So there's no solution. That must mean that this is the condition that has to be met or has to be true in order for y equal to e to the rx to be a solution. So that's the condition that we were looking for, that we can solve this particular quadratic equation. And it is a quadratic equation, so remember there's going to be three types of solutions. We can have one real solution, and I'm just going to write SOLN to abbreviate solution. You could have two real solutions. Or you may have two imaginary or complex solutions. So those are the three things that happen when we solve quadratic equations. Well, this particular quadratic equation, this AR squared plus BR plus C equal to 0, this is what we call our auxiliary or characteristic equation. Okay, and if we can solve that, then we can solve the differential equation. So again, this is just what that AR squared plus BR plus C is called. So we're going to go through and we are going to solve the three different types of differential equations. So all we're doing is finding the solution to AY double prime plus BY prime plus CY equal to 0. We'll look at this first case. Well, this first case says if our roots R sub 1 and R sub 2 of our auxiliary equation are real and unequal, so two different real solutions, then our general solution for our differential equation is of this form. Y of x equal to C sub 1 e to the R sub 1 x plus C sub 2 e to the R sub 2x. So notice that this is that general form that we looked at on the previous page under our theorem. Let's go ahead and look at an example. In example 2, we want to solve this differential equation 3 times the second derivative of y equal to 5 times the first derivative of y. Well, the first thing I want to do is I want to set it equal to 0 to get 3 second derivative of y minus 5 first derivative equal to 0. Notice that there's no y in there, but that doesn't matter. Now that I have it in the correct form, all I have to do is look at 3, the y double prime, that's your r squared, minus 5. Y prime, or the first derivative, is just r, and there's no y here, so we're just going to set it equal to 0. This is the equation that we're going to solve. So I can factor out an r to get 3r minus 5 equal to 0. Of r equal to 0 and 3r minus 5 equal to 0, which means r is equal to 5/3. So these are two different solutions. You could look at this as like an r sub 1 and an r sub 2 in the general form. So I have these two different real solutions. It must be true that my general solution is equal to some c sub 1 e to the r sub 1 would be 0x plus c sub 2 e to the r sub 2 is 5/3. And then I would simplify it. I would never leave this as e to the 0x. I would write it as y of x equal to e to the 0x, it's just e to the z, which is 1. So this is c sub 1 plus c sub 2 e to the 5/3 x. That is it. Let's look at the other condition. This would be condition 2. Let's just say we have one real solution for our auxiliary equation. if that's the case, then the general solution is going to be y of x equal to c sub 1 e to the rx plus c sub 2 x e to the rx. Okay. So again, one real solution, that's the general form. Example 3, we're going to solve this differential equation, 16 second derivative of y plus 24 first derivative plus 9y equal to 0. So the auxiliary equation is 16 r squared plus 24 r plus 9 equal to 0. So now this should factor as 4r plus 3 squared, or 4r plus 3, 4r plus 3. So notice that there are two of the same solutions, which means I just have the one solution, 4r plus 3 equal to 0. So r is going to be equal to negative 3/4. One real solution, the form is going to be y of x equal to c sub 1 e to the negative 3/4 x plus c sub 2 x e to the negative 3/4 x. And now we'll look at that third condition. The third condition is when you have complex solutions. So that would be where our auxiliary equation has complex numbers r sub 1. And here, instead of using the a and b, because we already used a, b, and c for our differential equation, so I can't use a and b again. So instead, we're going to use the Greek letters alpha, beta. So if one solution is alpha plus beta I, and the other solution is alpha minus beta I, these would be our two complex solutions. Remember, I is just your imaginary number. So in that case, the general solution y of x is going to be e to the alpha x times c sub 1 cosine beta x plus c sub 2 sine beta x. In example 4, we're going to solve this differential equation. Notice that this particular differential equation, if I look at the auxiliary equation, which would be r squared plus r plus 3 equal to 0, this is not factorable, which means I have to use the quadratic formula, which means r is equal to -1 plus or minus the square root of -1 squared. So 1 minus 4 times, remember it's 4 times a times c, which is simply 3, all over 2 times a. In this case, it's just a is 1, so it's just 2. This then becomes r equal to -1/2 plus or minus. This is going to be the square root of 1 minus 12, so the square root of -11. Remember, you take out the negative, that becomes the I, so it's just square root of 11 over 2 times I. The -1/2, that's your alpha, and the square root of 11 over 2, that's going to be your beta. It does not include the I. So beta is just the real numbered part without the I. And our general solution, again, all we're doing is plugging these values into our general solution, is going to be e to the -1/2, as it's alpha x, parentheses c sub 1 cosine of beta, which would be the square root of 11 over 2 x. And that's the argument on cosine. So if you want, you could put parentheses around that whole thing, but it's really not necessary. plus c sub 2 sine of the square root of 11 over 2x. So again, find your auxiliary. Don't forget to set it equal to 0. Find your auxiliary equation. It'll be quadratic. It'll either factor or it won't, and you'll need to use the quadratic formula to solve. So you're either going to have real solutions or complex solutions. And depending on the type of solutions you have, you're going to have a different type of general equation. So these general solutions or general equations that we find, remember, they don't have initial conditions. So now we're going to look at solving a problem with initial conditions, but we do have to be careful with second order differential equations. Sometimes, even if you have initial conditions, there still will not be a solution to your differential equation. So we call these equations, we call them boundary equations. So these are boundary value problems where they're going to be second order linear differential equations. We're going to have two initial conditions, one for the function itself, one for the first derivative, usually. So unlike our usual initial value problem, a boundary value problem may not be solvable. Okay, so even if you have initial conditions, there still might not be a solution to your differential equation. In example 5, we're going to solve the initial value problem, second derivative of y plus 3 times first derivative of y is equal to 0. So the first thing I'm going to do is set it equal to 0, but that's already set equal to 0. So the next thing I'm going to do is find my auxiliary equation, see if it's factorable. That would be r squared plus 3r equal to 0. And yes, this is factorable. So it's r times r plus 3 equal to 0. I have two real solutions, r is 0 or r equal to negative 3. That gives me the general solution, y of x equal to c sub 1, e to the 0x plus c sub 2, e to the negative 3x. And again, the e to the 0x is just 1. So my solution is y of x equal to c sub 1 plus c sub 2 e to the negative 3x. I do have two initial conditions. I have y of 0 is equal to 3 and y prime of 0 is equal to 3. So remember that 0 that we're putting in, that's an x value. If I look at my equation, that would give me, for y of 0 equal to 3, that's going to give me c sub 1 plus c sub 2 equal to 3. So I have a problem here. I have two variables, but one equation. I can't solve this. So now I'm going to use that second condition that y prime of 0 is equal to 3, only I don't have y prime. So I'm going to take my general solution and I'm going to take its derivative. So the derivative is going to be, so derivative of c sub 1 is just 0 since it's constant. And then the derivative of c sub 2 e to the negative 3x is going to be negative 3 c sub 2 e to the negative 3x. So now that I have my first derivative, I can go to that y prime of 0 equal to 3, that initial condition. So if I put in 0 for x and 3 set that equation equal to 3, I have negative 3 c sub 2 is equal to 3. and then c sub 2 has to be equal to negative 1. So now that I know that c sub 2 is negative 1, if I look back at the c sub 1 plus c sub 2 equal to 3, I must have that c sub 1 is equal to 4. All right, so I actually do have a solution. The solution is y of x, going back to my general solution that I got. Or maybe I don't want that one. Maybe I want the one where I simplified it. I found my c sub 1 to be 4. And then plus c sub 2, but that's minus 1. So it's going to be a minus e to the negative 3x. We'll just do one last problem, and then we're done for this section. Example 6, again, we're going to solve this boundary value problem. We have our differential equation, and we have two conditions. For this particular problem, notice that I just have y of 0 and y of 1. The initial conditions don't have anything to do with the derivatives, which is fine. We'll just proceed like we normally would. We're going to look at our differential equation. We're going to look at our auxiliary equation, which is r squared minus 6r plus 9 equal to 0. And now this factors as r minus 3 times r minus 3, or r minus 3 squared. So we just have one solution, which is 3. One real solution gives us y of x equal to c sub 1 e to the 3x plus c sub 2 x e to the 3x. And I have this initial condition that y of 0 is equal to 1. Plugging in, that gives me, let's see, if I put in 0, the c sub 2 term, that's gone because it's times x is 0. That gives me that c sub 1 is equal to 1, which is great. But I still need c sub 2. So I'm going to look at that second condition, that y of 1 is equal to 0, and maybe that will help me. If I put in 1 for x and then set the equation equal to 0, I get e to the third power plus c sub 2 e to the third power equal to 0. And then I can factor out the common e to the 3 to get 1 plus c sub 2. Again, we have e to the 3 equal to 0, or 1 plus c sub 2 equal to 0, and e to the 3 equal to 0 can't happen. So I know that this is not a solution, and I have 1 plus c sub 2 equal to 0, so c sub 2 is equal to negative 1. My solution is then y of x equal to e to the 3x minus x e to the 3x. And you solve all your boundary value problems this way. Find your auxiliary, find out your roots, your r's, and then given your initial condition, that would depend on how you would solve the problem. And that is it for this section and all the material of the course.